Welcome to this lesson on the conservation of energy. Today, we're going to explore energy transformations in mechanical systems, one of the most fundamental concepts in physics. Let's start by understanding the two main types of mechanical energy, kinetic energy and potential energy. Kinetic energy, often abbreviated as Ke, is the energy an object has because of its motion. We calculate it using the formula, Ke equals 1/2 times mass times velocity squared. Gravitational potential energy, or PE, is the energy an object possesses due to its position in a gravitational field. We calculate it using the formula, PE equals mass times g times height, where g is the acceleration due to gravity, which is approximately 9.8 meters per second squared, and h is the height above a reference level. Now, let's discuss the concept of total mechanical energy. When we ignore forces like friction and air resistance, the sum of kinetic and potential energy in a system remains constant. This is what we call the total mechanical energy. This concept is expressed by the equation total energy equals potential energy plus kinetic energy equals a constant value. This is actually a special case of the law of conservation of energy, which states that energy cannot be created or destroyed. It can only change form. Why does the conservation of energy matter? Well, energy transformations are all around us in everyday life. For instance, think about a roller coaster. At the top of a hill, the roller coaster car moves slowly but has high potential energy due to its height. As it descends, this potential energy transforms into kinetic energy, causing the car to speed up. Similarly, when you stretch a rubber band, you're giving it elastic potential energy. When you release it, this potential energy converts into kinetic energy as the rubber band snaps back. It's important to note that even when energy seems to be lost in a system, it's actually just being transformed into other forms like heat or sound. No energy ever truly disappears. This is the essence of the conservation law. Let's visualize energy transformation with a quick diagram. Imagine a ball being dropped from a height h. At the top, just before release, the ball has maximum potential energy and zero kinetic energy, since it's not moving yet. As it falls, midway down, some of the potential energy converts to kinetic energy. The ball is now moving faster, so its kinetic energy increases, while its potential energy decreases because it's now at a lower height. Just before it hits the ground, the ball has almost no potential energy left because it's close to a reference level, the ground, but it has maximum kinetic energy because it's moving at its fastest speed. This graph shows how potential energy and kinetic energy change during the ball's fall, while the total mechanical energy remains constant. Let's work through a practical example to see how we can apply the conservation of energy. A 2.0 kilogram brick is dropped from 5.0 meters above the ground. How fast is it when it passes 3.0 meters above the ground? First, let's identify our heights. The initial height, h1, is 5.0 meters. The height at our endpoint, h2, is 3.0 meters. Next, we note that the initial speed, v1, is 0 because the brick starts from rest. Now, we can apply the principle of energy conservation. The loss in potential energy must equal the gain in kinetic energy. We can write this as mg times h1 minus h2 equals 1/2 m times v2 squared minus v1 squared. To solve for v2, we can simplify. First, notice that mass m appears on both sides, so we can cancel it. Also, since v1 equals 0, v1 squared is also 0. This gives us g times h1 minus h2 equals 1/2 v2 squared. Rearranging to isolate v2, we get v2 equals the square root of 2g times h1 minus h2. Now let's plug in our numbers. v2 equals the square root of 2 times 9.8 meters per second squared times 5.0 meters minus 3.0 meters. This simplifies to the square root of 2 times 9.8 times 2.0, which gives us the square root of 39.2, or approximately 6.3 meters per second. Therefore, the brick's speed at 3.0 meters height is about 6.3 meters per second. Let's summarize the key takeaways from today's lesson. First, mechanical energy simply moves between kinetic and potential forms. It's a dynamic balance. In an ideal frictionless world, the total mechanical energy never changes. It's just redistributed between these two forms. When solving problems involving falling objects or other systems where only gravitational forces are doing work, we can use the formula 1/2 mv squared plus mgh equals a constant. Remember, understanding energy conservation gives you a powerful tool for analyzing motion without having to trace every step of the path or consider all forces separately. It's one of the most useful concepts in all of physics.